Our focus in the macQsimal project is the development of a pre-commercial miniature atomic clock, and we aim at bringing this first European miniature atomic clock with very competitive performances, very close to the market. World-leading partners like Aurelia Switzerland, CSCM and VTT are teaming up with their own respective system-level expertise to achieve this common goal, while the University of Neuchâtel brings expertise for even better performing future clocks.
The applications of such a clock are diverse. They range from underwater oil prospection to telecommunication network synchronization and even to use in small satellite in space. The development steps of the Mac prototypes are as follows. First, based on a review of the requirements, the miniature atomic clock prototype is designed. Here, the shape, material, and other properties of the clock components, such as the atomic vapor cell, the laser, or the packaging methods, are selected. Simulations are then carried out to verify the expected thermal mechanical properties of the Mac prototype, such that the design can be adjusted. A final design review is then conducted that validates the selected approach. Some of the parts are procured off the shelf, tested and validated, while others are developed, fabricated and tested within macQsimal. Examples are the atomic vapor cells fabricated in CSCM's clean room and ceramic parts fabricated by VTT. The assembly phase starts once all the components are available and validated. It begins by pre-assembly of the base package components. The assembly of the main optoelectronics component is then made by VTT. This includes the laser, the atomic vapor cell, and the photodiode. Finally, the optical waveguide is integrated by CSCM. At this point, the physics package assembly is mounted on a dedicated PCB for functional testing. Such tests are realized in a dedicated climatic chamber in CSCM premises. The assembly physics package is put under vacuum and controlled by laboratory electronics. Functional testing consists of measuring the atomic signal, measuring the clock resonant signal, and finally, locking the atomic clock and measuring frequency stabilities. Last but not least, vacuum encapsulation of the physics package is realized prior to integration into the clock systems by Aurelia Switzerland.
At Aurelia, we have three main tasks related to the development of the miniature atomic clock. First, at the beginning of the project, we define the specifications at system level. This includes the size, power consumption and stability of the clock. For this task, we use our more than 20 years of expertise as atomic clock manufacturer, and we also listen carefully to the requirements and feedback from our clients. Second, during the project, Aurelia is responsible for designing and fabricating the electronics and software for the clock. And third, towards the end of the project, we integrate the clock at system level. In this task, we also test the clock to validate that it meets all the specifications we defined at the start of the project. Finally, based on the test results, and together with our partners CSCM and VTT, Aurelia will analyze the clock technology and estimate the overall cost and maturity level for a hopefully future product launch.
At the University of Neuchâtel in Switzerland, within the macQsimal project, we focus on the reduction of fundamental clock instabilities for improved performances in future generations of miniature atomic clocks. The selected interrogation approach makes use of pulsed interrogation schemes for vapor cell atomic clocks. In fact, the laser light used to prepare and to detect the atomic quantum state also slightly perturbs the atomic frequencies. By switching off the laser light during the microwave interrogation, this perturbation is avoided and the clock stability can be improved. Finally, these schemes then have to be integrated into the miniature atomic clock prototypes while preserving its very small size, low weight and low power consumption, properties that are referred to as a low swap factor.